Imagine standing at the mouth of an impossibly long tunnel, a perfect straight line burrowing through the heart of our planet, slicing from one surface to the exact opposite point. You step in, and without a whisper of air resistance or friction, you begin to fall. At first, your acceleration is familiar, 9.8 meters per second squared. The ground seems to rush toward you. But as you plunge deeper, something remarkable happens. Gravity's pull begins to weaken, not because of the tunnel's walls, but because there is less mass beneath you drawing you downward. In this idealized world, Earth behaves like a uniformly dense sphere. At any depth, the gravitational force pulling you toward the center is proportional to the amount of mass enclosed within your current radius. Mathematically, if you are a distance r from the center, the force you feel is exactly the same as if all the mass inside radius r were concentrated at the center. Outside that radius, the mass cancels out, contributing nothing. The net effect is a gravitational acceleration that drops linearly with r, fading to zero the moment you reach the core. This linear dependence transforms your journey into something delightfully familiar: simple, harmonic motion. Just as a mass on a spring oscillates back and forth under Hooke's law, your motion through Earth obeys F, kr, where k encapsulates Earth's average density and the gravitational constant. You speed up until you hit the midpoint, then slow down symmetrically as you climb back toward the other side. There are no jerks, no turbulence, just a smooth exchange between potential and kinetic energy. Crunching the numbers reveals a surprisingly short trip. Plugging in Earth's radius and surface gravity gives an oscillation period of about 84.5 minutes. That means a one-way passage through the planet, from your start point through the center to emergence on the far side, takes roughly 42 minutes. In under an hour, you would go from one continent to another, purely under the pull of gravity, without engines, without fuel, without even touching a rail. At the very center, your speed peaks. Conservation of energy dictates that the kinetic energy you have equals the gravitational potential energy you've shed since leaving the surface. This works out to a maximum velocity near 8 kilometers per second, over Mach 20. In a matter of seconds, you'd flash past the speed of sound, then outpace it by a wide margin. Yet, thanks to the linear weakening of gravity, you'd never exceed that speed, because beyond the midpoint you decelerate under a gently increasing pull, coming to rest exactly at the other surface. In reality, Earth is not uniform. Its inner structure, crust, mantle, outer core, inner core, exhibits complex density gradients. A more accurate model replaces the simple linear GR with a curve derived from seismic data. Even so, the motion remains oscillatory, though the trip time shifts slightly. Numerical integration through the preliminary reference Earth model suggests that a non-uniform density adds only a few minutes to the journey, preserving the essence of the 40-minute transit while introducing subtle asymmetries in velocity and acceleration. And what of the energy required? Since the motion is frictionless in theory, no work is done against resistive forces. You convert gravitational potential energy into kinetic energy and back again, with perfect reversibility. In this thought experiment, the only energy you'd need is the initial nudge to get you off the platform. Then gravity carries you. This purely theoretical tunnel teaches us elegant lessons about gravity, motion, and the deep interior of our planet. It remains, of course, an idealization, a playground for equations and imagination. Yet, by exploring it, we glimpse the profound simplicity hidden within Earth's complexity, and we learn that sometimes the most ambitious journeys lie not in distant galaxies, but in the mathematical space of a perfectly drawn line through our own world.